It depends on what the function of the capacitors are. If they're filtering capacitors, then that might not be the problem, but it probably works off of, it would surprise me if it didn't work off pulse width modulation.
No,
Generate phase.
well, maybe with each phase it might, but how it ended up coming to be is we ended up having to call the tech support of the actual device itself, and the dude went through the whole process of elimination, and he's like, all right, there's two things wrong. Either your relays.
But most of this will be okay. We talked about series circuits, parallel circuits, what takes to make a circuit, the two different types of circuits that we have. We'll just go back here and talked about the different conductors. Of course, this is cable splicing, so that's something we need to know. The different metals we'll run into in metal conductors. That's in there. The PowerPoints are up there on Blackboard also too. So inside course content. So this is predominantly PowerPoint anyway. We don't have a book for the class, so you got to take really good notes, and of course depending on the PowerPoint. And also what we've done is this is in a fluid situation, guys, so I'm still working on this. So if you print it off, it's at your own risk. At the end of the term would probably be a good time to print it. But we've also got a glossary term that we use in this field. And I know the one I've got up there is a little different now. But this is over in course content, and then also in reference material. And then the glossary should be right here. So learning the language of the trade is very, very, very important. And the way it's set up is basically the course is split into two sections. The first section is metal conductors. And then the second section is fiber optic conductors. So the first 4 weeks we do metal, the second 4 weeks we do fiber optics. And so that's the way the glossary is set up. So the first part is what the terms that we would use in metal conductors. And then the second part is what the terms that we use in fiber optics. Now the first chapter, or first thing we'll look at, basically deals a little bit with both of them. And then we'll strap into nothing but metal and then nothing but fiber optics at the end. But so the second part is what we talk about, what will the terms that we'll use in fiber optics. Are we okay? So when you're reviewing for tests and it says know the meaning of the following terms, and this would be the place to go. Don't try to go through all the PowerPoints and try to learn those terms. Just go right here to the glossary to look at the terms. And like I said, I'll post the lecture, Tuesday's lecture up on Blackboard, and it's going to be inside that recorded lecture link, so make sure you go back and look at that. So we talked about series circuits a little bit, we talked about parallel circuits, we talked about series parallel circuits, and we looked at some symbols. So learning the symbols of your trade is very, very important. Well, I'll try to put a handout on symbols up there. Looked at the American wire gauge, which gives us the different size wires, but we're going to talk more about that in this class. And then talked about short circuits and open circuits. So this is like we were talking about last Tuesday. This is probably one of the most misused terms. Besides ground. Ground is a term that's really, really misused. but the other term is short or shorted. Most of the time you'll hear people that don't know different call any problem they have in an electrical circuit a short. How many times you heard that? Yeah, I got a short. There's a short in there somewhere. There's a short in there somewhere. Well, the problem is they don't understand what a short is. I'm driving along in my car and I run over a tracks and my headlights blink. What would you think that would be? Not going to be a short, because a short would blow a fuse. And my lights would never come back on. So that's the problem we have. So a short doesn't mean we lose current. A short is a what? Undesirable path. So we still have current flow. It's just that I've lost control of the path. So normally we like to control the path that the current flows. Short, what we've done is we've lost the control of that. Now what that means is that once we get a short, one of the big things is a short will always cause the opposition in the circuit to go down. And the opposition goes down, the current would go up. Okay. We got another term called a short. So we can have shorts and not have short circuits. Now, short circuit is for some reason the two conductors that apply power to my circuit. So we understand that every electrical device has to have two wires connected, at least two wires connected to it, right? You understand? So when we send power through a circuit, if we lose one of those wires, we call that an open circuit or an open. But if we connect those two wires that come from our power source, in DC we call it the source conductor and the return conductor. This is called a short circuit. Now the problem is the only thing in a short circuit, so what's current equal to? You learned that in intro. How do we calculate current? How do we calculate current in a circuit? Which we use I to represent current, right? How do we calculate current? E or V over R. E is another term we use for voltage. So you need to learn both of them, because in books you're going to run into both. So I could use E or V. E over R. Well, if I have a certain amount of voltage and then my resistance goes to 0 ohms, what's 0 divided into any number? Huh? What's 0 divided into any number? People don't understand what division is. So we learn multiplication tables and we learn division. We learn multiplication tables and we use those in division. But basic divisions is I would start off with a number. And we used to, when microprocessors first came out, they could not divide. They could add and they could subtract. That's all they could do. You had two instructions. One you could add and one you could subtract. So how would we divide? Well, we had to write a program that divided. So we had to come up with a way to come up, what is division? Well, division is subtraction. Multiplication is repetitive addition. Division is repetitive subtraction. So what we would do is we'd start off like with the number 5. And then we would start counting the number of times we could subtract. So let's say I wanted to divide it by 1. Well, I would come up here and I'd say, well, 5 minus 1 would be 4. 5 minus 1 would be, minus 1 would be 3. 5 minus 1 would be 2. 5 minus 1 would be 1, right? 5 minus 1 would be 4. 4 minus 1 would be 3. 3 minus 1 would be 2. 2 minus 1 would be 1. 1 minus 1 would be 0. 0 minus 1, we're through. Because as soon as you get down to going negative, it would stop. And then I would count the number of times I subtracted, and I would count 5 times. So what I would do is I would increment a loop every time I subtract. Well, how many times can I subtract 0 from 5? Now, how many times can I subtract 0 over 5 and not end up with a negative number? Infinite. So any number divided by 0 is infinity, which we don't understand, right? You understand. But it's a really, 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 really big number. So normally if you take your calculator out and you say 5 divided by 0, it's going to come up and say error. And why is that? Because it cannot represent infinity. If you ask Siri what's 5 divided by 0, she's going to cut you down. She starts off and says, imagine you have 0 friends or something like that. So you ought to do that on yourself. So if I come over here and I have 0 resistance, what would my current try to go to? If I have 0 resistance in the circuit, what would my current try to go to? Infinite. It can't go to infinity, right? Because your power source is only able to put out a certain amount of power. And if you exceed that, then something's going to happen. Or your wires are only available to handle a certain amount of current. So if you have this is a short circuit. Y'all understand that? So what limits the amount of current in a short circuit? Well, number one, it's the power source. Somebody's going to give up. Or the conductors. Somebody's going to give up. Either the power source or the conductors. One of the two is going to give up. Now, normally what we do is we put a special conductor in there that we call an overcurrent protection device. In your house, we usually call those circuit breakers. And then, of course, we also have fuses. Hopefully, those are the guys that give up the ghost. Somebody's going to give up. Okay, y'all understand? Yeah, they're a lot cheaper to fix. Can't you imagine? Most everybody's had a short circuit in their house. And Alabama Power don't want to give up. You know, Alabama Power can put out gigawatts worth of power. So who's going to give up in your house if you have a short circuit? Your wires. And what they're going to do? Yeah, cause a house fire. So definitely in your house you need an overcurrent protection device, either a fuse or a circuit breaker, right? So we have a short, so I can have shorts and not blow fuses, or pop breakers. But if I have a short circuit, hopefully you have an overcurrent protection device, or somebody's got to give up. If you got a little old tiny battery, C-cell battery, the battery gives up usually because it just can't put out enough current. Now, Alabama Power can put out plenty of current, right? Huh? What's that? Yeah, power. So what happens, what creates shorts is we have incorrect. So the name of the course is Cable Splicing and Installation. But what does splicing mean? It should be called cable splicing termination. So we do two things with conductors. What's the function of the conductor in a circuit? What is the function of the conductor? You can't say a charge, because voltage is a charge, and we don't carry power. Wires don't carry power. What does a water pipe do? Carries water. So what does a conductor do? Carries current. So that's it. What produces power? You can't have power. You got to have two things to have power. Right? What do you got to have? You got to have a voltage, and you got to have a current. Now the load, it's actually a voltage drop. You got to have a voltage drop. Okay. So, but the function of the pipe and voltage does not move. So what does the water pipes do? Carries water. What does conductors do? Carries current. Well, what's the function of it? Who does the work? Who's supposed to do the work in the circuit? What's the basic parts of a circuit? What's the basic parts of an electrical circuit? A power source? Well, not really a power source. A voltage source.
Yeah.
Conductors and load. So what's the function of the conductors? To the load. Okay, y'all understand. So what's the function of the conductors? It's to carry the current to the load. Now once the load flows into the load, then the load produces the power. The currents are not supposed to consume any power. I wish that was true. But they do. They do consume power. And why is that? Yeah, they're not perfect. I think we can. I don't know if that's in this slide or not. Well, and so what we end up with is we end up with this little chart right here.
Yeah, with the last column.
Yeah, so when we give out wire gauges, so wires are gauged, and this is called the American wire gauge, and this is the gauge that we'll be using. We also have the European wire gauge, which uses millimeters. Some of your wire gauge charts use both. This one does, in fact. So we still call it the American wire gauge, but they also look for what? The millimeter. Now what they do is they assign a number to a diameter. So a 20 gauge wire would have a diameter of 32 millimeters. And that would be the cross-sectional, that would be the diameter of the wire. Now, what do you notice right off the bat?
The higher number is smaller the wire.
Yeah, the higher the number, the smaller the wire. So when we say you need to go to a bigger gauge wire, we're not talking about the gauge number, we're talking about the size of the wire.
Yeah,
right? You understand? That's right. But we don't say that. We don't say you need to go to a smaller number wire. We say you need to go to a smaller size. But most people say you need to go to a smaller gauge wire, right?
Yeah.
Which means they're going to a higher number. So the number is just a number that's assigned, and there's a math formula, by the way. So the American wire gauge goes from like numbers down to 50. The biggest number we have in the American wire gauge is what we call a 4/0. Playing with 4/0 would be fun too. So 4/0 has a diameter pretty close to half an inch. So you try to bend a half an inch of copper solid. We don't see very many call it this solid strand. Most of your big gauge wires are going to be stranded, and we'll look at that in a minute because you're talking about a rod up there. We'll talk about the advantage of stranded over solid. But we also come over here and look at this column right here. What's this say here? It's the resistance value at 1,000 feet.
Yeah.
Now, unfortunately, they don't show it in this table. I think the next, they don't show it in this table. But this is at so what determines the resistance of the wire is, number one, is the material it's made out of. And number two is the size or the gauge. Number three is the length. And number four, which they don't list there, is the temperature. And the way it responds is temperature goes up, resistance goes up. Directly proportional. So you could take a piece of wire and you can measure that resistance, then you could use the change in resistance to measure temperature. Huh? No, a thermistor is silicone. But what we do is we can take these things and we can wrap them around a piece of ceramic, and we just wrap them in a loop and 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 get a real long resistance. And then we end up with a temperature sensor called an RTD. Yeah, which is a resistive temp device. Yeah, because if it's directly proportional, the only problem we have with RTTs is they're real slow.
Yeah.
They don't respond real fast. But if you're using something that doesn't respond real fast, then RTTs work real fine. Like your oven. Of course, your oven don't use RTTs, it uses thermocouples. But like your water heater. So when you start heating up your water, it takes a while for the water to heat up. So RTTs work real fine, work real good in there. So if a wire has resistance, and then we push current through that, power is equal to voltage. Well, power is equal to I square R. That's the one we here. Yeah. So what happens is if the conductor has resistance and we push current through resistance, what does it produce? It produces power, it produces heat. And if the wire gets hot, what happens to its resistance? It goes up. Now, if the voltages don't change, then we have no problem. But if the voltage changes, we have a big problem. We'll talk about that. So here's our power formulas, which y'all didn't get to in the intro to engineering. The main power formula, where the other power formulas came from. So Ohm's law has three formulas that we solve for different things. And the main one is voltage is equal to I times R. And then we can put that in a wheel or a triangle, what do you want to talk about, where we put V at the top, and then we put I, R here. And then what we can do is we can just cover up what we want to solve for. And this is a formula you need to learn. Ohm's law. V is equal to I times R, I is equal to V over R, and R is equal to V over I. Those are Ohm's law. The problem we have with Watt's law, so this is called Watt's law, which is power is equal to force times distance, times speed. Now in electricity, so you can look up in any physics books and you'll ask them about power. And they'll say power is equal to force divided by distance, or it's going to be equal to force times speed, because distance and speed are inversely proportional to each other. So when we get into electricity, we use the same formula, except in electricity, our force is voltage, and then our speed is current. Huh? No, there's no distance to power. There's no R in power. Power, to calculate power, it's force times divided by distance, or it's force times speed. Y'all understand that? Well, electrical wire, it's not, we don't want it to produce power, but it does. It's just like your blood vessels drop pressure. So one of the main things they do when you go into your doctor's office is they check your blood pressure. And if you start getting blockage in there, then of course your blood is your current, right? You understand that? And what's the loads? Muscles. Yeah, your loads are your muscles. So your brain is a load, right? So that's why, and we deliver that blood to your brain, and when it flows to your brain or your muscles, then that's the work, right? You understand that? Does that make sense? So resistance is not in the formula it's not in this formula for power, but we can get it in there. So what they did is they say, well, Ohm's law says that V is equal to I times R. So what does that mean? Well, that means, so two $5 bills is equal to $10. So if they come up there and they say, okay, that's $10. And I say, well, dang, I don't have a $10 bill. I'm screwed. But you got two fives. So what does that mean? They are equal to each other. So two $5 bills are equal to each other. So that means instead of having a 10, I can replace it with two fives. So if Ohm's law says that V is equal to I times R, that means anywhere I see V, I can replace it with what? I times R. So let's replace it right here. So I'd say, okay, P is equal to V times I, right? I'm sorry. I'm replacing V. P, oops. I'll get this in a minute. I'll still get it in a minute. I keep hitting erase. So I'll come up here and I'll say, well, P is equal to I is equal to what? I times R times I. So what would we call that? We got two I's. What do we have when we have multiply? Yeah, so we come up here. So another formula we got is P is equal to I squared R. I don't know. That's supposed to be a times. I just got it too close together. But I don't have to put times. So that gives us another power formula. Now I can come in and substitute I. I can substitute what I says Ohm's law, what Ohm's law says I is equal to. So Ohm's law says I is equal to V over R. So now I can come down here and use my main power formula. So power is equal to V times V over R. So that gives us what? Power is equal to V squared over R. So our three power formulas are what? Power is equal to V times I. Power is equal to I squared R. And power is equal to V squared over R. And then you can take and rearrange these. So you can imagine this would have three deviations, this would have three deviations, this would have three deviations. So there's 9 formulas you'd come up with in Watt's law. So that's pretty interesting. By the way, what you need to understand is that this R can be substituted by any of these guys right there. And we'll look at that a little bit. This becomes a little more important so we can explain that. So we have 3 types of opposition in a circuit. We have resistance, which is what you learn about in intro to engineering in DC, because in a DC circuit, that's all you have, is R. In AC circuits, we pick up 2 more oppositions called resistance, we call impedance. We pick up 3 more, one we call impedance, one we call capacitive reactance, which is the XC, and the other one we call XL, which is inductance. We'll have to understand that a little bit. You'll get it into really big detail if you take AC, and this class will give you these terms just to understand what goes on in a conductor in an AC circuit. Are we okay? So in DC, you'll learn about resistors. In DC circuits, there's only one opposition, and that's R. But AC changes around a little bit. Summary, and this is where we're at. So all circuits must have resistance. If not, according to the previous formula, the current and power will theoretically go to infinity. So I is equal to V over R, V over 0 would be infinity. Power is equal to V times I, so that'd be V times infinity. So your power would probably go to infinity. Current flow will never go to infinity. If load is bypassed, the current flow circuit will be limited only by the resistance of the inductor, the internal resistance of the voltage source. If we don't protect this by an overcurrent protection device, what does that mean? So what we have is we have these power supplies. So this is a battery. That's not true. This is the symbol for a DC voltage source. So this guy right here is an electronic power supply, and it's a DC voltage source. But this guy produces DC electronically. So we bring AC in, then we convert it over to DC electronically. Batteries produce DC chemically, right? You understand that? So, but this is the symbol for a DC voltage source. Most people, you say, what? Once you get through DC and say, what's that symbol for? And they say, well, it's a symbol for a battery. And that's not true. It's a symbol for a DC voltage source. So all our DC voltage sources would use the same thing. A symbol for an AC voltage source is a circle with a squiggly line in the center. So this is a symbol for an AC voltage source, and this is a symbol for a DC voltage. Now, the problem we have is that a voltage source has an internal resistance. There's no such thing as anything that has zero resistance. And if you put current through a resistance, what happens? It drops the voltage. You don't understand that? So that means I can come over here and I can get, and we might do that, I'll go get a battery. I can go over here and have a D-size battery, or even a AAA would probably be better, and I put a resistor across it, and I was looking at the output of the battery would drop. Well, what's causing the output of the battery to drop? It's internal resistance. It's internal resistance, not the resistor. It has something to do with it. It sets the I in the circuit. But as soon as I hook up a regular battery, across a load, right? So go out there on your car, put your battery across there, don't crank your engine, and turn on your headlights. What's going to happen to the output of that battery? It's going to drop. What's dropping that voltage? The internal resistance of the battery. That makes sense. Y'all understand that? So when we come up and we do electronics, what we could do with these voltage sources is we can do what we can regulate them. We can do this with electronics. So that means I can take the output of your alternator, and of course there's in your power system in your car, you have an alternator. And then you have what we call a rectifier assembly. That's an assembly that converts AC to DC. Your car runs off DC. Y'all understand that? Everybody, y'all understand that? So your alternator generates AC. Then we have an electronic circuit we call a rectifier circuit that converts it from AC over to DC. But I can go out there and I can crank the engine on my car. And I can go out there and measure the voltage with my meter. And it'll measure a little over 14 volts. And I can turn on my I can turn on my lights and it's 14 volts. I can turn on my air conditioner and it's going to be a little over 14 volts. But what's happening to the internal resistance of my alternator? Is it changing? No. What's happening is our regulator is putting more energy. It's doing a technique that we don't talk in this class. But what it does is the regulator looks at the output, and if the output tries to drop down, it puts more energy into the system and makes it go up. If it tries to go up, it takes away. So what happens is if we got a regulated if we got a regulated voltage source, the output maintained is fairly constant over the range of its operation. But if I come over here and do this, what's the output of what's it going to drop to? Now it's going to depend on the internal resistance of the voltage source, and now the regulator can't take care of this, right? You understand? There's no way in the world it can put out a voltage that would put a voltage into 0 ohms, but it's not 0 ohms. But what it's going to do is it's going to try to increase that energy level as high as it possibly can. The current available in the output will be as high as it possibly can. And the only thing limiting the current is the resistance of the source and the resistance of the wires. Now what's going to happen, what happens on a regulated voltage source is this wire starts getting really hot. And what happens to its R? It goes up. Well, now we got a higher R, so what's your regulator going to do? It's going to raise this voltage up a little more. It's trying to shoot for the maximum output. So what happens on these regulated voltage sources is as the resistance of the wire goes up, you're thinking the current's going down, but it's not. Because the regulator keeps doing what? Going up. And the wires get hotter because now you got a bigger R, right? You understand. You still got the same maximum current. You got a bigger R, the wire gets hotter. Its resistance goes up. Your generator's trying to put out 14 volts. Now it can put out 3. This resistance goes up. Your regulator's saying, hey, I can put out a little more voltage. It'll go up. And the current's the same, right? You understand. And the wires get what? Hotter. So what's going to happen eventually? Wire's going to burn up, or your alternators. So somebody's going to give up. So what happens? Somebody gives up. Now, if you got an unregulated source, it's usually the voltage source that gives up. So I could come up here and I can get a AAA battery and I can take a wire and put across it, and the output of the battery goes down to 0. Because now the internal resistance of the voltage source gives up. If I've got a regulated power supply like this, as the resistance goes up, the voltage goes up because it's trying to regulate at a certain voltage, right? You understand? So he usually gives up in a regulated power supply system. Usually the wires. Unless we do what? Unless we protect them, right? When all loads are circuit, this is called a short circuit. Short circuits are bad. Somebody's going to give up in a short circuit, right? I guarantee you your car battery's not going to give up. So what's going to happen in your car if you have a short circuit and you don't have it protected? The wires are going to disintegrate. You got big problems. Your alternators. So we know about overcurrent protection devices. What's our overcurrent protection device? The two main ones we use. Fuses and circuit breakers. What's the advantage of a circuit breaker? You can reset it. What's the advantage of a fuse? Cheaper. By the way, what we do is we literally, the fuse is made out of a metal that melts at a fairly low temperature. And we already know that that fuse has a small R. Very small. In fact, the bigger the fuse is, the less the R. Your small fuses, like your 10 milliamp fuses, those guys might have 10, 15 ohms. But you're not putting hardly any current through them, see, right? You understand that? Your big fuses, like your 15 amp fuses, you measure those are going to measure almost 0 ohms. But it's still got ohms. And what happens when you push current through ohms? Power is equal to what? I square R. What does resistors do with that power? What does resistance do with power? What does it produce? Starts with H. Heat. Yeah, so resistors, that's what they do with their power. The power a resistor produces is heat. That's the power it produces. So we've got a piece of metal in my fuse. It's got a very low melting temperature. It's got an R. I push current through it. Who's going to give up? The fuse is going to give up. It's going to melt. And that's what fuses do. They literally melt. We call them blow. The fuse is blown. But that's what they do. It melts. And of course, when it melts, it creates what we call an open circuit. Now, a circuit breaker has different means of operation. The primary means is by heat also. It uses what we call a bimetallic strip that heats up the pinion and causes it to trip. But once they cool off, what can you do? You can reset them. So fuses are really, really cheap compared for the south. Yeah, go down to Lowe's and look at a 15 amp breaker and look at a 15 amp fuse. One of them's probably going to be less than $1. The other one's probably going to be $10. So circuit breakers are quite expensive. These are commercial residential circuit breakers. I've offered these guys. These are in your houses. So you go out to US Steel or someplace like that, you're going to almost see no circuit breakers because they use a ton of fuses. The fuses that they use normally has a replaceable fuse link inside there. We don't have over here. If it was over motor controls, I could show y'all. But what happens is your two end caps on your fuse twist off, and you replace the link. So you don't replace the unit or tube that thing's in, which saves a pretty good deal of money. So this is a short circuit. I'm sorry. This is a short. So notice one of the loads is bypassed. Now, is this a short circuit? No. Now, the current in load 4 will go up. So a lot of times a short will cause other components in the circuit to fail. But the current in load 4 goes up because the resistance in this path right here goes down. Okay. The current through this path stays the same. But if the current in this path goes up, you can see the voltage source is providing two loads. So it's coming over here and dividing this, and then of course it comes through here and then comes back, right? So what we have here, this is what we call total current. So that means your voltage source has to provide all the current for all the loads on your system, right? You understand? So what happens is that, so this might be 1 amp. And without the short, this might be 1 amp, but when it goes, so if it was 1 amp, then my IT would be 2 amps, right? Does that make sense? They just add together. Are we okay? You okay, James? Well, if we had a short and this goes up to 2 amps, because we've lost this load, then my total current's going to go up to 3 amps. So any short will cause total current in the circuit to go up. But this is not a short circuit. This is a short, right? You understand? So that's a short. This right here would be an example of a short. That would be an interesting to figure out. This would be an example of a short. This is what we do a lot. People solder. Y'all be doing some soldering in this class. And they splatter solder on their circuit board or where it's not supposed to be. Now you got a conductor inside there, right? So a lot of these shorts like it are caused by us, just not doing things right. This right here is a short circuit. So notice the difference. I could have put the bar here. I could have put the bar there. But what we do is anything that where we connect the two conductors that come from the voltage source, if we connect those two conductors together, this is a short circuit. So what do we need to do to keep these guys from connecting together? Well, one thing we use insulators. What's an insulator? Bridge shorts and short circuits. Imperative that the conductors in a circuit are isolated from each other. Substance that isolates the conductor is called a what? Insulator. Insulators are made from substances that exhibit extremely high opposition to current flow. We don't say infinite. We got to understand that in our world there is no such thing as infinity, even though we say it. We don't understand infinity. Infinity goes how far? Forever, yeah. So we don't understand infinity. So that means if I've got a path and I've got a voltage source, then I've got a circuit. So when insulators have extremely high opposition, so is there current flow through the insulator? Yes or no? Yes.
insulator? Well,
There is current flow. It's just that it's so low that we can't measure. But there's current flow through insulator. Guaranteed. Huh? Minute, yeah, very minute. An open allows no current flow through the load. If no current flow, no work is performed by the load in which the open is. An open circuit permits current flow through the entire circuit. So we can have an open, thank goodness. Because if we created an open circuit, I couldn't go over there and turn off a set of lights because everything would go out. So when you're in your house and you don't have something plugged in, you're creating an open, right? You're not creating an open circuit. But when you turn off a light switch, you're creating an open circuit. So if I come over here and turn one of these switches off, what I just created is I created an open circuit. Right, you understand? So all those sets of lights over there are on the same circuit, and I created an open circuit. See, all the lights are off of there. So I created an open circuit, right? Understand? Oops. Oh, wait a minute.
too many opens.
We had a couple of. But one of these bulbs up here could blow, and that would be an open, right? You understand that? All the other lights would stay on because it's parallel.
The whole thing parallel?
Yeah. Yeah, all the lighting like this is in parallel. The only lighting I know that's in series is Christmas light. An open circuit prevents current flow through the entire circuit. Sources of opens, of course. We create opens on purpose. We don't create shorts on purpose. Normally. Not normally. We do sometimes in digital. Digital's pretty neat. We can create shorts in digital, but they're designed to handle it. So we don't normally create shorts. We very seldom create short circuits, even though I've seen it done before. I've seen electricians, they'll get into a place that none of the breakers are labeled. None of the breakers are labeled. And they can't turn off everything to figure out which one does it. So they'll deliberately create a short circuit. I've seen them deliberately put wires in a plug, trip the breaker. So they can do what? Figure out where it goes. And in that way, they don't have to kill everything. Now, my wife don't like it when I do that either. So when I got into my house, not a single breaker was labeled.
You've been creating a lot of shorts.
No, I didn't create shorts. Luckily, it was a house. It wasn't any life or death situation. You know, so I went in there. So that would be like I'm working at a business and you got 100 computers in there and they're all on different circuits. And I go in there and kill everything. Well, that company's just totally out of business, right? Or I'm in a hospital place. That would be a situation where you might create a short circuit. In my house, it's no big deal. So what I would do in my house is just do what?
Turn it off.
Yeah, turn it off and see what goes on. So on-off switches, we deliver fuses and circuit breakers. These create open circuits. Faulty splices. So a splice. So the function, and I got off track a while ago. So a splice, we have conductors. And what's the function of the conductors? Carry the current from the source to the load. That's their function in life, to carry the current from the source to the load. We can't have conductors that are infinite in length. So what does that mean? And if a wire breaks, we don't normally go in and replace the wire. what we do is somehow we connect the two rope slides together, or when we run out of spool of wire, we get another spool and we connect the two spools, the ends together. Connecting conductors together is what we call splicing. So we'll learn different methods that we can splice metal conductors and different methods that we use to splice fiber conductors. Fiber's a little more touchy. Now eventually, all conductors have to come to an end. Y'all understand that? Well, because once they get to the load, the conductor's job is over. Now the load is not a conductor. The load is what's using the current to produce the power. The art of bringing a conductor to an end is called termination. So when we connect a wire to a circuit board, or we connect it up here to the lights up here, that would be terminating. We have different methods we use to terminate conductors. And of course, we know excessive current will cause conductors to melt, right? So we get melted conductors, that's also going to cause opens in the circuit. So this is an example of an open. So what we've done is we've lost this set of loads. So load 3 and load 4, they're still doing their job, right? You understand? This is what's nice about parallel. Parallel means we can create opens and it don't affect anybody else. So that means I can go out and turn the lights off in my kitchen and it don't affect the lights in my living room. I can leave a wall outlet unplugged and it don't affect anything else, right? So I can go over and look at that wall. I got something plugged in over there only on one of them. There's 3 of them that has nothing plugged in them whatsoever. Well, it's no big deal. It's just that now the voltage source does not have to control or provide the load for that device. So what would happen is total current in my house would go down. This is why you create opens all the time. You don't create open circuits, you create opens all the time at your house. So you go in there and turn off the lights, then the power that was produced by that is no longer having to be supplied by your voltage source. So in a circuit like this, as we remove loads, your total current goes down. Your voltage don't change across here. And this is a big thing people don't understand. So if that's 120 volts, then it's going to be 120 volts whether I have something plugged in or whatever, anything that's connected to this wiring. So that's why you can go to any outlet in your house and you can measure across the outlet and you're going to measure whatever your house gives you. Right? This would be an open. So when an open, total current goes down. This would be an open. This right here would be an open circuit. So where's your circuit breakers at? They're not out here. They're right there by the source, right? So you have a panel box. So you got your down drop coming down, or however you get your power into your house. It goes into your power meter. Your power meter feeds your panel box or your breaker box, and then everything else goes out past your breaker. So your breakers are in series with everything else, and they create what type of circuit? Open. But what's so nice is I could come out here and put a switch right there, and then I could turn off those without turning off the others, right? So this would be a series parallel circuit. So we don't. The way your house is wired up is it's wired like this. We call this a parallel circuit. Except sideways. This would be an open circuit. Voltages across an open and a short. All the applied voltage will appear across a series open. Voltage across the short, not a short circuit with negative pressure. Go ahead and take a break while I bring up this power pole. 10 minutes. And like I said, I have no idea where James is at. Well, he's on his motorcycle. Most people on motorcycles get stuck in traffic or go down the center. Hopefully nobody opens the door. Go real slow.
Yeah.
Go down the center. Go down.
Well, there's one time where I was headed to work and someone was stopping one of them, and there's a third car in front of that one came to a stop, no reason whatsoever, and I wasn't able to stop. So I ended up sharing the lane, going around, and getting in front of that one car, and just acting like I'm.
Now people don't understand motorcycles don't stop real fast. They only got two wheels on the ground.
Yeah.
And you got to be real careful the way you apply your brakes.
If you don't apply it properly, you lock the brake, and you're in a worse situation.
Yeah, but after a while you learn it.
Yeah, when I first started riding it, I locked my rear brake. After I got used to the pressure on the brake.
Well, you should hit your rear brakes first too. Rear brakes, front brakes.
Yeah.
Because if you hit your front brakes right, your rear brakes, your bike wants to spin around on you, which is dangerous. So front brakes and then rear brakes. I never understood why they didn't put one brake pedal for both controls. Of course, if you're racing, you brake differently depending on what you're doing.
Yeah, you want to start first.
Yeah, we get brake front first, so I guess that's the only reason I can think of why they didn't put one brake pedal for both situations. Of course, what you do is that if your rear end wants to break loose, you can let go of the rear brakes. But it takes a technique. It takes a technique.
Yeah, I mean, I've kind of got down where I'll always use my engine brake and my front brake before I do.
Oh yeah, I gear down. I would gear down before I would brake.
Well, I'll gear down, and if I really have to stop, I'll gear down on my front brake, and if I just absolutely have to,
The rear brake, right?
I say for the rear brake.
But yeah, you slide easy. It's just like riding on these dang interstates where they're getting ready to pave it and they groove the road. Have you rode on that?
No,
Your bike wants to follow the grooves. It's a weird feeling. So you got to be careful on those.
Yeah.
A lot of times they'll put a sign up there about motorcycle beware. And reasons we don't take Windows XP off those computers because our version of electronic workbench does not work with Windows 7.
There is some other
Yeah, we've looked at some of those. One of them's really neat because it actually shows you the current flow through the circuit, and I got that one somewhere. But this is the one that I'm most familiar with, and I know. So let's see, docs, EET, cable spots and insulation. I don't see electronic workbench. We'll do these with a DC voltage source. And we'll do it with resistors. Even though y'all understand there's a lot of loads besides resistors. The only place I really know commercially that they use resistors as the load is incandescent light bulbs. That's all they are, just basically resistors. But they're metal. So when does the light bulb usually blow? when you turn it on. You ever notice that? Because you're dealing with something that has very low, it's usually tungsten. Tungsten has a pretty good R to it, but it depends, mostly it limits its current by heat. So when you first turn it on, it's got fairly low heat, so it gets a real shock, and then it heats up real fast, and then the resistance goes up. And then, of course, electric heaters. Electric heaters uses resistors. That's all electric heater is resistors. It's a resistive wire. If you look at them, it's wire, but it's not copper. It's not one of the real good conductors of electricity. So it's using nickel or nickel stuff like that, which has a pretty good resistance, huh? No, tin has a real low melting temperature. In fact, tin has a lower melting temperature than lead. But we use tungsten. Tungsten is used in incandescent bulbs. So tungsten has a pretty good R component to it too. I thought I had these circuits saved, guys, but let me look in before I do this. Let me look in the DC folder. That might save us a little time to drop my. So DC, we usually deal, let's see, electronic workbench. Opens and shorts. So there we go. Oops, messed up. So what we can do with this, so this is what we call a series circuit. So notice on a series circuit, we have multiple loads. And they're all connected one into the other. And of course, when you get into DC, this will be, you'll look at, in intro, all you look at is one resistor circuits. When you get into DC, you'll look at what we call series circuits and parallel circuits. So Christmas lights are wired in series, or it's actually a series parallel circuit. So when we turn this on, so I'm going to come and turn the simulation on. And this is my voltmeter. And we got it set up on DC. And then we can come over here and oh, here it is. It's down here. So there's my voltmeter. So if we, and then this is actually where we can actually read it at. And of course, first thing we do is check our units. We got it on volts and we got it on DC. And so if I measure across the circuit, in fact, what we'll do is, this is the way we would normally make our measurements. Normally we reference one of our leads to our circuit common. So a lot of people don't understand that. What we do in electronics is we got to have at least two conductors. Well, what we do is we use to represent one conductor symbol. This is a symbol for what we call ground. So what we did is we're calling this our common of our circuit, not the common of our meter, the common of our circuit. So instead of drawing the wire, we represent it with a symbol. But what you have to understand, everything, there's still a wire there. It's just that the less wires I draw in a schematic, the cleaner the schematic is. So what we do is we replace the wire with a symbol. That makes sense? So a lot of people don't say, well, I thought that was inside, but it's a wire there. And if we come over here and measure the voltage source, so I'm going to come over and put it right here. Or try to put it right there. Or I can put it right here too. So, so I'm going to connect it right here. And then, of course, right now it's turned on, but it says I have 0 volts. Now, why do I have 0 volts? Got it open, right. We got it open. It's an open circuit. So up here we have a switch. And I'm going to come up here and I'm going to close the switch. And now it goes up to 12 volts. So we deliberately create open circuits by using a watt, by using switches, right? You understand that? By the way, it takes a minute. We okay? Now what happens is when I go through a load, we drop some voltage. So on this side of the resistor, we have 12 volts. I didn't break my circuit. Let me do away with it right here. I might have. I did. So on this side of the resistor, I have 12 volts. On this side of the resistor, I'm going to have less. Oops, my simulation turned off. So here we have 10.15. So that resistor is dropping about 2 volts. Right? That makes sense? Yeah. And we can measure with our meter. Our meter, this lead right here, this will be what we call our black lead. This lead does not have to be connected to circuit common. We can literally come up here and connect it across something, and we can measure the voltage drop. Now here I hooked my meter backwards. Well, not backwards. I have the minus, the black lead towards the positive, and I have the positive lead towards the negative. So my meter is negative. It's not a negative voltage. It's just the way I have a meter. And what it does, it makes it a lot easier. So that resistor is dropping 1.8 volts. And then I can come over and take it and put it across this resistor. And this resistor is dropping 4.1 volts. So what you should notice is the bigger the resistor is, the more voltage that it drops. And then I'll come over here and move this lead right there, and that resistor is dropping 6 volts. So you notice the biggest resistor drops the biggest voltage in the series circuit. And then of course if I put it across all the resistors in the series circuit, it's going to drop all the voltage because all the voltage has to be dropped within the electrical circuit. So notice now my meter measures 12 volts again, right? Does that make sense? So what happens if we come over here and open one of these resistors? So I'm going to come up here and notice we can put a fault in here. Oops. So we can put a fault in here. So let's come up here and open this. So now we have an open. Of course, so this tells me it's there. And notice when I come over here and look at the other devices in my circuit. So a while ago, this resistor dropped 6 volts. What does it drop now? That's 0. It's just negative. So it's dropping 0. Why is it dropping 0 volts? There's no current. Still has resistance, but to get a voltage drop, V is equal to I times R. If I have no I don't care how big the resistor is. If I have no I, it's not going to drop the voltage. That makes sense, James? I'm going to come over and look at this one. This right here is dropping 0 volts. Why is it dropping 0 volts? It's a 2.2 k ohm resistor. Well, V is equal to I times R. How much is I? 0. So what's 0 times the number? What's 0 times the number? 0. So it drops no voltage. So even though it still has a resistance, it drops no voltage. Now watch what happens when I come over here and put it across the open. It measures the applied voltage. Now why does it measure the applied voltage? Because nothing's dropping any voltage. So that means if that 3.3K drops no voltage, it's like moving this ground right there. If this drive drops no voltage, it's like putting that ground right there. So what happens is if we have an open in a series circuit, the entire voltage appears across it. So if I come over here on this light switch, what would it measure across the light switch for all these lights that are on? Well, how many volts would it measure across the light switch of all the, with these things on? Yeah. Oh my goodness. Well, let's see, how much resistance does a switch have? Nothing. So V is equal to 1,000 amps times nothing. So how much voltage is dropped across a closed switch? Nothing. No voltage across a closed switch, right? You understand? What if I open that switch? It's going to measure applied voltage because nothing in the circuit is dropping any voltage, right? You understand that? So we measure across a open in a series branch, we measure the applied voltage. Across a short, how much resistance does a short have? 0. That's what we're doing. We're creating, basically what we do with a switch is we're creating a small little short right there, right? You understand? It drops no voltage. So we'll prove that. So we'll come over here. So let's write these down. So this guy right here, I'm going to take the fault out of this one. And we can do the math. I'm going to no fault. Okay, I'm going to turn the simulation back on. And notice it's dropping 1.85 volts. Let's write that down. 1.85 volts. So that's R1. R1's dropping 1.85 volts. There's no problem in our circuit. R2 is dropping 4.1 volts. And then R3 is dropping 6.1 volts. Oops. Okay, so we can come over here. Let's do this too. Let's come over across my switch. My switch is closed. And how many volts has dropped across my switch? None. I'm going to open the switch. And what's dropped across the switch is my software updates. 12 volts. So how's it dropping 12 volts? I've got all these resistors out there. How could it drop 12 volts when Ohm's law, up until now we said resistors drop a voltage, and people don't understand a resistor only drops a voltage if there is a current flow through it. So if this guy here drops nothing, that means that's literally taking this guy and putting it right there. If this drops nothing, that's literally taking this guy and putting it right there, right? You understand? If this guy drops nothing, that's taking this, putting it right there. If this drive drops nothing, so this is why the applied voltage appears across. So we don't really say it drops voltage. It's just the entire voltage appears across the open. because nothing else in the circuit is dropping any voltage, right? You understand? So loads are acting like a straight piece of wire. That's what they act like. So even though right now, if I measured across this switch, it's going to measure 0. If I went over and turned it off, it's going to measure 120 volts. So what do we need to do now? We need to create a short. So in a series circuit, every open is an open circuit. So this is why when you got Christmas lights, they're series parallel. So you might have 20 lights in a series string. When one of the lights goes out, what happens to all of them? They all go out because it's a series circuit. So in a series circuit, any open is an open circuit. So let's come over here and short this resistor right here. So notice one of the things we can do is short it. This is not a short circuit. This is a short. And then we'll turn our simulation back on. What should the voltage be across the short? This is troubleshooting, guys. What should the voltage be across? How much should a short drop? Nothing. Yeah. Of course, this is a simulation. Oh, the switch is open. So this guy is showing, what's that? That's 2.2 microamps. Well, this is a simulation. Yeah. Microamp, I'm sorry. And then, of course, so if it's dropping a no voltage, that means your other two resistors are going to have to make up the difference. So a while ago, what was R2 dropping? R2. R1, we know now it's dropping nothing. It was dropping 1.6 volts or something like that. What was R2 dropping, James? You write that down. Okay, so right now it's going to make up the difference. So its voltage drop is going to go up. So it's gone up to 4.8. And another one's going to go up to about 7.2 volts. So what that meant is power is equal to I square R. So R2 gets a little harder, R6 gets a little harder. This is what we're talking about. In a series circuit, sometimes a short will cause other things to fail. So usually in my series string, if I don't have a spare bulb, I just pull it out a little bit and twist it, and two wires short together, and all my other lights come back on. But what you got to understand, instead of dropping 2 volts, each one of them is dropping a little more, which makes them a little more susceptible to blow. You ever did that? Series string, find the one that's open. It's hard to do, guys. Normally what I do is just get a good bulb that I know is good of another string, and I just start swapping it down the line until I find it comes back on. So that's a short. Now let's do a short. So how to do a short? There's only one way we can do a short. What I'm going to do is I'm going to make all these guys a short circuit. So that means they all have 0 ohms. And now when I turn it on, what should happen? Nothing. Oh, I got to turn it on. Then what should happen is my fuse blows. Now let's come up here and take the fuse out and create a short circuit. Okay. What we're going to do now is look at our current meter. What does our current meter say? 96 kiloamps. This is a simulation. Of course, my battery wouldn't put out 11.9 would put out 12 kiloamps, right? You understand that? My wire wouldn't handle 12 kiloamps.
Wires pretty thick there, sir.
real big, and that's a heck of a battery, probably as big as this room right here. So this is the problem we have, is that, you know, your current tries to go to infinity. It can't go to infinity for number one. We'll never go to the fusion because we got two R's. We have R of the source and we have the R of the resistance, or the R of the wire. But we got that I square R. Normally, if it's not a big battery, your battery is unregulated, but odds are it would not give up. Not unless you took a jumper cable and put it across your battery. And then you need to say a little prayer, because your battery would get extremely hot, and it would get extremely hot real fast. It's got water in it. What water do when it gets hot? Expands real fast. So when you short out a battery, that dang battery, a car battery could blow up on it. And that's not good. Because not only do you have shrapnel heading at you, you got acid heading at you too, right? So please don't short out your car battery. Yeah, some of your car batteries have 200 or 300 cranking amps, and that's how much they can put out for a short period of time. So don't take a jumper cable and put it across your car battery. And please honor those polarities on your jumper cable. Because if you hook it up one way on one battery and hook it up the other way on the other battery, you still got a short circuit, right? So let's open all these, and then we'll go down to the parallel circuit. Oh, not open them. We'll make none. So what's nice about electronic workbench is we can't kill anybody with electronic workbench. So this is what we call a parallel circuit. You can see why it's called parallel circuit. So what happens here is we come up, and that's misconfusion. So in parallel circuit, in electronics, we call each one of these branches. In electricity, they call everything that's hooked to a circuit breaker, they call it a branch. So that's a little different right there. What we got is we got an ammeter here, and right now we have no faults in the circuit. So let's open the circuit. And so we got an open circuit that we produced with a light switch, with a switch. And we'll start off by making our measurements relative to circuit common. And we could hook up to any one of these, and I'm going to turn the power on. And of course, it's measuring 0 volts. Why is it measuring 0 volts? So we created an open purpose, right? An open circuit. When I close this, my meter goes up to 12 volts across that load. And that would be the current flow up there. If I put it right there, it's going to measure 12 volts. Oops. You can see why, because this is a straight piece of wire. Here comes my voltage source. This is a straight piece of wire. If I put it right here, this measures 12 volts. If I come over here and put it here, this measures 12 volts. So what we'll do first is we'll turn it off and we'll create an open circuit. It takes a little while for the simulation to update, so we'll create an open. This is not an open circuit. This is an open. And then we'll turn the simulation on and we'll close our switch. First, let's take the open out. And let's record our current. So our current is 21.1 milliamps. So I'm going to come up here and open this load. And notice my current went down to 9.1 milliamp. So in a parallel circuit, the voltage across them are the same. So that means your smallest resistor conducts the most current, produces the most work. But this is not an open, this is an open circuit. Now what am I going to get when I measure across that? Well, you're still going to get 12 volts. Opens in parallel circuits are harder to find. In a series circuit, it's real easy to find because in a series circuit, it drops the applied voltage. In a parallel circuit, it's going to drop the applied voltage whether it's open or shorted, right? I mean, whether it's open or not. So notice I still have what? Still have 12 volts. Still have 12 volts here, still have 12 volts there. So what's changed is the amount of current flow in the circuit. So I'll come up here and take this one out here. So none. And then we'll open this one. This is still not an open circuit. But the current drops down, see, so in a parallel circuit, the smallest resistor does the most work. In a series circuit, the largest resistor does the most work. So what you're going to learn is you're learning series and parallel circuits are just opposite from each other. In a series circuit, the biggest resistor drops the most voltage. In a parallel circuit, the resistors drop the same voltage. But what's nice in a parallel circuit is I can do what? So in a parallel circuit, an open is not an open circuit. But what doesn't it affect? What doesn't it affect? It don't affect the other loads. But anytime I have an open, total current always goes down. In a series circuit, it goes to 0. In a parallel circuit, it depends on the load. And that's why at your house, you try to turn off everything that you're not using, because if your current goes down, since power is equal to V times I, if your current in your house's drawing goes down, then the power consumed goes down and you pay less. So you're always telling people to turn off stuff, right? You'd be surprised how many people electricity has problems with that, especially after you learn series circuits. Now what happens if I have a short in a parallel circuit? So I'm going to short this resistor right here. So I'm going to short this resistor. I opened my switch so it wouldn't happen instantly. So right now R2 is shorted. Got shorted on it. Somehow it's shorted. And then I'm going to come up here and I'm going to close my switch, and as soon as I do it, the fuse blows. So in a parallel circuit, every short is a short circuit. But an open is not necessarily an open circuit. So I created an open circuit. If I create an open circuit, what happens to the current flow in the circuit? If I create an open circuit, if I create an open circuit, what happens to the current flow?
Created open circuit.
The current flow goes to 0. So how much work are we getting? None. No power, no heat. So this is why your circuit breakers and your fuses are connected in series. So in a series device, when it opens, you create an open circuit. In a parallel circuit, if you create an open, it's not an open circuit. In this one we got 2 others, but at my house it means I can turn off a light and it don't affect my refrigerator or my oven. It don't affect my other house lights. It don't affect my air conditioner because your house is wired parallel. Electronics use not only parallel circuits, they use series circuits, and they use what we call series parallel circuits in electronics. But power is delivered in parallel. because of this reason. So we can do what? So I can unplug my Christmas lights. My garbage disposal still works. But if my garbage disposal shorted, or it was a short, it would pop the breaker, and I would lose everything on that electrical branch. Are we okay? Shorts and opens. Now shorts happen. Loads short. Things happen. People let wires get too hot. The insulation burns off the wires. The two wires touch together. We have a short circuit. Things break. Termination. We don't terminate a wall plug correctly. We don't screw it down good enough. We don't clean it off. It has an R. We push an R. It's supposed to have almost no R. It has an R. We plug in our vacuum cleaner. It pulls a lot of current. Now at my terminal, I have an R. It gets hot. Copper. What happens to copper when it gets hot? Well, it oxidizes. Rusts real fast. Copper oxide is an insulator. Now I've added more R. I push current through R. It gets hotter. Now all of a sudden it exceeds the heat rating of my insulator. My insulator gets charred. It starts burning off. Then it touches something else, and now I got a short circuit. And my breaker pops. But it popped at 15 amps, but I put a 20 amp breaker in there and it don't pop anymore because the R is still there, right? You understand? Now my house burns down. Because I had a circuit breaker that was popping all the time, and I went down Lowe's and bought a 20 amp breaker to keep it from popping. And my wire's rated at 15 amps. Well, for NEC, 14 gauge is actually rated over 30 amps. But NEC rates it at 15. And we'll look at that. Huh?
Me and my dad bought this like a PVC oven. We're modifying it to be able to put PVC sticks in it.
And either melt them or soften them up.
Yeah, so we can fit March. And wires 14 gauge. I thought that was weird. It's never oven that is very mechanical. So I'm like, it should be 12 according to NEC.
Should be 12. Well, odds are you're okay, because when they rate a 14 gauge wire, they're rating it for worst case scenario.
Yeah, and I don't know.
But they shouldn't have done that. Whoever, I don't know how, is it UL approved or somebody built it?
I think it actually was. I don't know how that got passed.
I don't either.
Usually they check everything.
Yeah, they check everything.
It's weird.
So y'all got any problems with that? Y'all okay? Shorts and opens. Coming back to you? If you just had intro, you hadn't talked much about that. DC and AC. We have two types of current. We have direct current and we have alternating current. A direct current flows in one direction. The electron from DC circuit flows from negative terminal to the positive terminal. Right. The big advantage we have off of DC has got a couple of big advantages. It's very easy to produce chemically. AC we can't produce chemically, so it's very easy to produce chemically. And the other big polarity is the second little knot down there as well. We can electronically control DC. Produced by DC generators, produced by batteries. DC generators do it through magnetics. DC batteries do it through chemically. Thermocouples do it through heat. Solar cells do it through light. Piezoelectric devices do it through force. We can do it electronically using AC to DC converters, which is exactly what your automobile has in it, right? You understand that? And then we can do it bioelectric. So lightning bugs. We are bioelectric devices. Our brain processes electrical impulses. Well, where do those electric impulses come from? Well, it comes from us. We create it chemically. We create electricity chemically. And y'all watched, what was that name? The Matrix? The Matrix, what would we use that as in the Matrix? Batteries, yeah. Are we okay? What, James? Electric eel does it. Electric eel is a unique device in that it can produce both DC and AC. So most people understand voltage cells. Most people call them batteries. Basically, a battery is a group of more than one. So technically, AAA batteries and AA batteries and D batteries, these shouldn't be called batteries. They should be called cells. And what we do is we take cells and we hook them either in series or we hook them in parallel to create batteries. 9-volt batteries are batteries. Those are true batteries. If you broke those apart, you'd find 6 cells inside there. Little individual things built, sound like a car battery. You see them isolated between each other with a little slip of paper. DC generators, solar cells, which these are photovoltaic cells. Piezoelectric, most people see these lighters that you can strike the piezoelectric crystal with a force and it creates electricity. Thermocouples do it from heat. And I didn't put alternating current. Constantly swaps direction. The voltage source in the AC constantly swaps polarity, which causes the current to change direction. The big advantage of AC is less expensive to generate. It's extremely efficient to transmit power. Voltage can easily be, what we can do is we can change the level of the voltage by using transformers. And AC motors are a lot less expensive for horsepower than DC motors. These are created by AC generators. So DC exists in nature, right? Understand? AC. So DC was discovered. AC was invented. Who invented AC? Nikola Tesla. And more since the Tesla automobiles came out, he's become more well known, but a lot of people know who Edison is. So Thomas Edison worked with DC. He didn't discover DC. Ben Franklin discovered DC. Edison popularized it and also refined it too. And then Nikola Tesla invented AC. So your car is an alternator, it's an AC source. Mobile generators are AC generators. Power plants create AC. DC to AC converters. A lot of people buy these things for your cars. That's AC. My wife's van's got one built into it. So she's got a 120 volt plug in her van where she can plug stuff in. And of course, things called function generators. These create AC electronics. So what they do is they take AC, they convert it to DC, and then we use that DC to electronically recreate AC. So it's really neat. That's what a function generator does. Are we okay? So AC creates a really neat waveform, and for reasons, it varies. So AC is generated on a circle or created on a circle. And how many degrees in a circle? 360. So what we do is we create let me make sure I have this on a sine wave. And this is a device called an oscilloscope. And what's neat about an oscilloscope is it shows us exactly what's going on there. Your meter would not measure this, but okay. So what I've got is I've got this function generator that generates that. I got this function generator, and I don't even have my camera software open. So sorry guys, this will take just a second. Oops. So this is my function generator. So this is a device that generates AC signals electronically. So we bring in Alabama Power, or not here, TVA. We bring in TVA, we turn it into DC, then they electronically recreate AC. But what I can do with this, which I can't do with Alabama Power, is what happens if I can change the voltage level. I've done something, guys. I don't know. I don't know what I'm doing. I'm gonna make this ready. Device. This is called an oscilloscope, and this gives us to visually look at what's going on with the voltage and time in a circuit. And I don't know what's happened to my function generator. It's not working. Oh, I do know what's happened. What did you say, James? Oscillation is, of course, oscillation is a generic term. So we have things that oscillate. Oscillate means they just go back and forth, back and forth, back and forth. In AC or in semiconductors, we have a circuit we call an oscillator, and an oscillator is a circuit that takes DC and converts it into a AC sine wave or a waveform. So what we can do with a function generator that we can't do with Alabama Power is I can come up here and I can change the rate. So Alabama Power does what we call 60 cycles a second. Let's see, with this I can change the cycles per second, and I can also change the amplitude. Now, how can I do that? Well, I can do that because I'm taking AC and converting it to DC, and I'm taking DC and converting it to AC. But what I can do is I can electronically control the DC, right? You understand? So one of the big advantages of DC is that we can electronically control it. So that means I can go out and buy an inverter for my car, and I can hook it up to my battery and run my AC drill on it because we're doing it electronically. We're recreating AC electronically. So what they do is this creates a waveform, and it's generated on a circle. So if it's generated on a circle, notice it constantly repeats. Wavelength is a physical measurement. So that means if I was to shoot this out a piece of copper wire, these waves would be at a different point down that copper wire all the time. And if I measured that, that would be what we call a wavelength, right? There's a formula for that. And we'll talk about that when we get into fiber optics, by the way. So we'll have to learn that when we get into fiber optics. But here what we talk about is this is voltage. And these things are occurring at a certain rate. Okay. Let me change this to hair. Make it easier for us to see this. Sorry, every time so what I'm trying to do is get this to cross on the line so we can see it a little better. Okay. So this would be what we call one repetition. You see it's got the vertical lines on here. Let me make them a little sharper so y'all can see them. One thing, so y'all can see the lines real well now, right? We'll bring the scope a little closer. Our camera. So y'all. So this right here would be one repetition of a repetitive waveform. Now these things go on forever. The only way they would ever disappear is if I turned my function generator off, or if Alabama Power or TVA cut us off here. So this one repetition of a repetitive waveform, we refer to this as a cycle. And that cycle has a certain amount of time. So if you look down here, this is my time for each one of these divisions right here. Time goes this way and voltage is this way. So this is my time. So that says 25 microseconds per division. So that'd be 25 microseconds. This would be 50 microseconds. Right? Understand? This would be 75 microseconds. And that would be the time for one cycle. 75 microseconds. Now, and we call that the period. So the time for a cycle is called the period. Now these guys are occurring at a certain rate. The rate we call frequency. So Alabama, if I was to take this scope and hook it up to Alabama Power, we would see the same signal because they generate AC on this type of waveform. It's just that their cycles, Alabama cycles, run 60 cycles per second. What we can do is that we can let our scope, this scope is a computer, so I could cheat and let it do it for me. But what you have to understand is if your time goes down, your rate goes up. If your rate goes down, if your time goes up, your rate goes down. So what we can do is we have this thing called the reciprocal. So frequency is it's the inverse of time. So we have this method of taking what we call the inverse or the opposite, or we call it taking the reciprocal. And we do it so much in engineering that every calculator has a reciprocal key on it. It's either going to be 1 over x, or it's going to be x to the minus 1. If you raise any number to minus 1, you get the reciprocal. So getting the reciprocal is another name we use for getting the inverse. So it means if I come over here and say 5, and then I take, so there's on this calculator, there's the reciprocal key. It's going to come up here and say 0.2. 0.2 is the opposite of 0.5. I'm sorry, not 0.55. So it means if I take this time, which we measured as 75 microseconds, and I say 75 times 10 to the minus 6, and then I take the reciprocal of that, it tells me that the frequency is 13,033 hertz, or 1.3 kilohertz. Now, if I come over here and look at my camera, this function generator has a special device in it called a frequency counter, so it's going to display the frequency for me. So what we did, we just calculated it, right? You understand? And I'm going to come over here and look at my camera, and I'm going to put it over here in my function generator, and what does it say my frequency's at? 13.35, and I have it on the Kellic scale. So the frequency and the period are exactly opposite of each other. So my oscilloscope does not measure frequency, it measures time. But it's real easy for me to just take the reciprocal of it and get the time. Now, so this would be 306, so one cycle would be 360 electrical degrees. So the cycle would start at 0, and then this right here would be 90. This right here would be 180. This would be 270, and this right here would be 360. But 360 of one cycle is 0 degrees of the next one. So it's just like 12 midnight. What's 12 midnight? It's the end of one day and the start of the next. Exactly 12 midnight actually has two meanings. It's the end of this day and the start of, it's the end of Monday and the start of Tuesday, right? You understand? So 360, and by the way, you can measure 360. You could start 0 degrees on the positive going edge, or you could start it on the negative going edge. It don't make any difference. By the way, y'all can't see this. It didn't focus real good. But this right here is representing 0 volts. So that means the voltage up here, this is a positive voltage. And voltage down here, this is a negative voltage. So what would happen to the current flow? If the current flow is negative to positive, this way it would be flowing back toward me. When it went down here, it'd be flowing away from the source, right? You understand? So what's the current doing? It's sitting there swapping. This is swapping every 75 milliseconds. How much work do I have right here? I have no work. So I have 0 volts. If power is equal to V squared over R, I have 0 V, right? You understand? By the way, if you divide into 0, you get 0. So we get no work. Now, what's going to happen is going to average this out, and we call it RMS, which we'll get into a little bit in here. So if I was to take that voltage and multiply it by 0.707, that would give me the work I'm getting. So these lights right here, believe it or not, these guys here are turning off 60 times a second, 120 times a second. But what does our eyes give us? It gives us the average, right? It averages it together. Thank goodness our eyes do that, or we'd have a problem watching movies. Because y'all know movies, there's nothing but what? A series of pictures. But they flash them at you so fast, your eyes just do what? Just average them together. Well, what we can do is if I was to take a vertical and drop it to this and go it over, we would form a right triangle. And we can solve for the different sizes of a right triangle using trigonometry. You don't have to learn that in AC. What we would say is that we could calculate where that thing would be up this edge right here if I knew the angle. So let's say 45 degrees. Well, if I knew what this voltage was, which we call VP, if I could take the sine of that angle, it would give me that exact voltage at that point right there. So what that means is this waveform varies with the trigonometric sine of the electrical angle. So we call this a sine wave. So that's how it got its name. Whether you understand it or not, but that's what it is. So the instantaneous voltage varies with the sine of the angle. So if you took, so here's my voltage right here. It's 5 volts per division. So what my peak voltage would be 10 volts, because that would be 5 volts, that would be 10 volts. Well, what that means, if I was to come over here and say this would be 90 degrees, if you took the sine of 90 degrees, it's 1. If you multiply 1 times 10, you get 10. The sine of 180 degrees is 0. So if you multiplied 0 times 10 volts, it would come up and give you 0. The sine of 270 degrees is a -1. If you took 5 times -1, it's going to be -5. So that's what we mean. So anywhere on this angle, I could take the angle and I could calculate what we call the instantaneous voltage. So what do they call this waveform right here? They call it a sine wave. And this is what Alabama Power generates. Yeah, Alabama Power generates sine waves. Or I keep saying Alabama Power because that's what I have at my house. Here in Bessemer, the power is TVA. So we're getting our power from Tennessee Valley. How in the world do they do that? So this is AC, and that's what we went over. Everything's in the next few slides. So this is a sine wave. How do you get the name? The instantaneous voltage varies with the sign of the electrical angle, right? And everybody okay with a cycle? What's the cycle? It's one repetition of any change in waveform. So we use this in DC too. So in DC we have what we call square waves or digital clocks. Well, digital clocks have a frequency. It's a repetitive pattern. So if I come over here and convert this over to DC, I mean, this still has a repetitive pattern. This would be one repetition. This is called a what? A cycle. The cycles are occurring at a certain rate, which would be a frequency. So when you get into computers, they talk about the speed they're operating at, and they use term megahertz or gigahertz because, by the way, I didn't talk about that, James. I'm sorry. In physics or in sciences, usually the people who are fundamental in the science, they get the honor of getting their name applied to, like Ohm's law. Well, how did they come up with Ohm's law? Well, Ohm's was a guy that was fundamental in the study of electricity. Kirchhoff's law, Watt's law. Well, the rate of frequency. So what's a cycle? Well, that would be what is a cycle? It's one repetition of a repetitive waveform. One repetition of a repetitive waveform. I left the E out up there. So one repetition of a repetitive waveform. And this is in y'all's glossary, by the way. What's the period? The time it takes for one cycle. And what's the frequency? This is the rate of the cycles. Measured, I don't have enough room, in cycles per second. So over here in the United States, we use 60 cycles per second. Most of the European countries use 50 cycles per second. And it varies. So we use 50 or we use 60, depending on where you're at. Frequency, I can't remember Hertz's first name, but it's spelled H-U-R-T-Z, equals cycles per second. So normally people will say 60 hertz. And it's uppercase H, lowercase z. That's why you abbreviate. That's why we're supposed to abbreviate hertz. So a while ago we got 3.3 kilohertz. That's why we would say it up here. So most of the time they give it in hertz. But hertz stands for what? Cycles per second. Are we okay? So cycle is one repetition of a repetitive waveform. Period is the time it takes for a cycle. Frequency is the rate of the cycles measured in cycles per second or hertz. And this is the terminology right here. So it's on the slide. One repetition of a sine wave, and that's not exactly true. It's one repetition of a what? A repetitive waveform. Because we run into a lot of other repetitive waveforms that are not AC. Alternation, each half of the sine wave, we call that an alternation. So we have a positive alternation and a negative alternation. Frequency is the rate of the sine wave curve, or the cycle curve, in the period of time it takes to complete one cycle. And it's abbreviated as time. Time is 1 over frequency, and frequency is 1. Are we okay so far? Three-phase. Three-phase generates power, or generates voltage or current. So generators generate voltage. And then, of course, how big the generators, or how big the... so what determines... So the way we produce electricity, and unfortunately I don't have this over here, but over in the motor control labs we have a nice big magnet. But one of the main ways we generate electricity, especially AC, is we take a conductor and then we move it through the magnetic field. So this is a magnet. And what that conductor does, when it cuts those lines of force, it produces a small voltage, which also is technically called an electromotive force. A lot of people call this an EMF. And that's why some formulas, when they represent voltage, they would use E. Are we okay so far? Now, what happens, if I come over here and run that wire, we end up with one little cell like that probably puts out almost no voltage at all. So what happens when we hook batteries or voltage sources in series? What happens when we hook voltage or cells in series, or even batteries in series? The voltage adds, right? So if this was 1 volt, and this was 1 volt, if this was 1 volt, and this was 1 volt, then I would get 4 volts. I would measure 4 volts when I whip that wire through there. But it's got to be cut in the field. So when it got on this side, it would be 0 volts, right? You understand? Well, if it comes back the other direction, then I'm going through the magnetic field, and what would happen is the current would reverse, but we would produce the same voltage. So what we do is we come up here and we loop the wire. So every loop is going to induce a little voltage, and they're wound in the same direction. And if they're wound in the same direction, then their voltage would add. So what happens if we hook batteries in parallel? So in series, they do what? They add. So what adds up here? The voltage adds. Yeah, up here the current adds. So when you get your remote, some batteries in series, some of them parallel. The ones hooked in series, we use that to get a higher voltage. The one hooked in parallel, we get this more current, right? You understand that? Everybody okay so far? So what they do in your generator is they put a bunch of coils of wire. They hook them, every coil will give us a different voltage, and then they add together, which would get our voltage up. So what determines the amount we get out of there then? You should know this. Yeah, that we induce into that wire. Well, first of all, it's the strength. First of all, we got to have this. This is what's required: a magnetic field. Not yet. We got to have a conductor. And then we got to have motion. Now, what determines the amount, if we go down this list, is the strength of the field, number 2 is the number of conductor coils. So each loop, we wrap them in coils. We don't just string them out, they're actually wrapped. And number 3 would be the speed of the motion. And how much current, what determines the resistance of the this would be the gauge of the wire. A lot of people say, well, all this does is gives you the amount of voltage that's available. But you got to remember, if you push current through a wire, if a wire has a resistance, it's going to drop a voltage. So this is why your big high current generators have a lot of coils of wire, but it's a big gauge wire, right? You understand? Because what we're trying to do is trying to reduce that current. But it's got to use a lot of wire because the only resistance it gets is the wire itself. So if I go back and forth, or if I come up here and spin this, like this, then out here it's moving in the same direction. It's not cutting the wire, so we get 0 volts out. We get our maximum voltage right here when this is perpendicular, and then over here we change direction. So what would happen is this guy right here would generate one of these. It would generate a sine wave, which is AC. And I guess this is where the 360 electric degrees came from, because when you go through 2 poles, originally when you went through 2 poles, you generated one sine wave. Now what they do to make it more efficient is they have hundreds of poles. And this would be a north-south. Well, when it goes through here in that north-south, it generates a sine wave. So we get multiple sine waves per revolution. And what we want to do that for is we want to run the slower we run our generators, the longer they're going to last. So if you ever watch an Alabama power generator running, you can see that sort of run. I mean, it's not running real fast, but it has a bunch of poles. And every time it goes through a north and a south, it generates 360 electrical degrees. But when they first did it, they just did a north-south, and I guess that's where they came up with electric degrees at. I don't know, guys, but it makes sense to me. Huh? Not in generators.
Well, if the running generator is slower, that means less power to run it. Like you put in the torque in it, but it's like you'd be a little more efficient that way.
What, to run it slower?
Run slower with more poles.
That's what most generators do. I don't know how many poles your alternator has, but you can take it apart, and every 2 of those gaps up there is a pair of poles. And so every time it goes through there, and I don't know, this is a problem we have with cars. Cars is constantly, our alternator is constantly varying what? The speed of the motor. So if you're sitting there idling, your alternator's running at 1 speed. You sit on the gas, your alternator runs up. Well, it wants to put out a higher voltage. But what we have the ability to do is we have something called an electromagnet. And I've got one here, guys, we can put up. But an electromagnet, what we can do with the electromagnet is we can do this. We control the watt. We can control the strength of the field. So what happens, what your regulator's doing is it's looking at the output of your alternator. If it tries to drop down, it increases the strength of the field and makes the voltage come back up, right? If it tries to go up, it decreases the strength of your magnetic field and makes the voltage go down. So what your regulator and your alternator is doing is constantly changing the strength of the magnetic field so your alternator puts out the same voltage. This is what we call regulation. That's what we have to do on this. It's a regulator. So I can't change the number of turns. To change the number of turns, I'd have to literally take my alternator apart, Once I've got the turns ratio set, it's set, right? You understand that? And of course, and the speed of your alternator is constantly changing. So what do they do? And what do your regulator do? What does your regulator do? It changes the what? The strength of that magnetic field. We have two ways we do this. We can do it using single phase. Do y'all need a break? You okay? So single phase requires 2 wires, or we can do it in what we call 3 phase. Which means it requires at least 3. Sometimes they use 4 if they run it. So 3 phase is going to be a lot more expensive because we're adding another wire. But what we do with 3 phase, so this is 3 phase. Oh, my other slide is better. I thought I had that up here, guys. Let me bring up another PowerPoint. No, this is the one. I think I opened up the wrong one. I need to get rid of the ones that's I'm not using anymore. I have a tendency to do that, though. It's kind of like when you're in programming. When you're going to make modifications to your program, you always make a copy of your own. Because if you get in there and screw up, you can always go back to the way you was. Guys, I don't know what it's doing. Y'all go ahead and take a break. Because I got some animation in there that somehow electromotive force. Did I write down something? We need a conductor. We need a magnetic field. We need a conductor. And we need motion. So anytime we put current through a conductor, we create a magnetic field. And if we can concentrate that field, then it helps out a lot. So this is nothing but a metal screw or bolt, and I have a bunch of wires wrapped around it. So anytime we put current through a conductor, it creates a magnetic field. And then what we do is we wound the magnetic coils in the same direction, and the magnetic fields add together, and then we wrap it around a chunk of metal to concentrate the magnetic field. And if we come over here and we put a voltage across this, so this is what your alternator uses, guys, or your generators. We used to call them AC generators and DC generators, but the problem we had is when the cars first came out, they had DC generators on them, and everybody called them generators. So when they went to the alternator, because it was more efficient, they didn't want to call it AC generator because people would get the term generator confused. So they started calling it an alternator. But in the electrical field, you have AC generators and you have DC generators. You don't have alternators. Oh, I got to turn it on. I got to plug it in. Somebody unplugged my power. So hand it to. Oh, here we go. So the X-Acto knife here, this is made out of steel. This wouldn't work on aluminum. And what I'm going to do is I'm going to turn my power supply on, my DC power supply. And these new alligator clips got right there. And what we notice when I get this down close to it, there it is. Now what we can do with an electromagnet, so this is an electromagnet, what I can do with it is if I change the current, then it would change the strength of the field. Another advantage we have is I can come over here and turn it off and do what? Turn it on. So anytime I put electrical current through a wire, it generates a magnetic field. Now this is constant, this is DC. Okay, y'all understand that? And of course I can control the strength and I can turn it off and on. So everybody's seen in the movies or actually around where they have these scrap cranes that swing over, got this big old puck out there, and they drop down and pick it up. Even within the James Bond movie with them. One of the first ones, right? So what we do with AC's got a change in magnetic field. So what happens is if I can put a change in magnetic field through a wire, and then I wrap it up in a coil to concentrate the magnetic field, and then of course in a transformer they would have it around a core to concentrate it even more. This magnetic field is sitting there going out, 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 in. Now if I bring another coil of wire in contact with that, like this coil of wire, if I expose it to that magnetic field, so when it's coming out of this other core, it's going to cut this and going to go back, it's going to cut this. I have a conductor, I have a change in magnetic field that's got motion to it, and I induce a voltage into this guy. So watch what happens. I'm going to come over here and take this. It's hooked up to AC. I got it across my function generator. And I've got an LED out there, and all I'm going to do is just place on top of it. You'll see? Magic. There's no electrical connection between these two wires. See my LED? So there's my LED back here in the back. I'm going to place the wire on top. What do you see? You know, take it off, it goes off. What did I just make? So there's no electrical connection, guys. So here's my function generator. So this is what we call induction, where I can induce a voltage into another coil of wire by just using AC. This only works with AC. DC has no what? It has no motion. But there I'm using an electromagnet, but I'm constantly changing the magnet. I'm changing the polarity. So what happens is that it goes positive, maximum current, swaps to zero, swaps around, the magnetic field goes out and keeps swapping back and forth. So now this is not very efficient, of course, because I don't have a real good coupling over here. In fact, on my electromagnet, if you look at it, it's got a special wire called magnetic wire, which means it's got almost no insulation on it at all, because the closer I can get the wires together, the more I get coupling. And then here I have a steel bar concentrate the field. Here I'm using an air core. So my transformer is very inefficient, but it still works. So what did I just make? Well, I made a device called a transformer. So I've got a transformer. Transformers only work with AC. Now what matters is that these ratio between, I have no idea what this ratio is, by the way, is this guy right here. This is the one that's connected toward the source. We call this the primary. This coil of wires right here we call the secondary. Now what determines how much voltage I get induced into that, and if I had a real good coefficient of coupling, which means how good we couple those magnetic fields, the turns ratio between the primary and the secondary would determine what my output voltage was. So that means if I had one for every 2 turns in my primary, I had 1 turn in my secondary, then my secondary would give me half the voltage. So if I put 100 volts over here, I get 50 volts over there. But vice versa. If I had 2 turns on my secondary for every 1 turn on my primary, then if I put 100 volts over here, I get 200 volts over there. So with transformers, we have what we call step-up transformers, and we have step-down transformers. So why do we want to step the voltage up? Well, Alabama Power is not delivering current, they're not delivering voltage, they're delivering power. So we have this magic formula where we have power is equal to V times I. But what Alabama Power, so what happens when I'm at my house and I turn on a 100-watt light bulb, my power company has to give me 100 watts. But they don't have to give it to me at the voltage at my house. So this is the magic formula right here. I is equal to P over V. All I did was move that formula around. So if I'm trying to give you a certain amount of power, the higher I can make that voltage to deliver that power, what goes down? Current. And the amount of voltage drop I get in my wire, I is equal to V times R. What determines the amount of resistance a wire has? The size of the wire, the material of the wire, right? You understand, and the temperature of the wire, and the length of the wire. So there, Alabama Power is trying to give you that power through a wire. A wire has resistance. If it's got resistance and I put current through it, it's going to drop a voltage. So the lower I can make that current, the less voltage my conductors, the higher I can make that current, the less voltage my current will drop. My conductors will drop. So what does Alabama Power do to transmit power? Well, they step the voltage up what? Real high. And then they transmit it. So the advantage of high voltage over low voltage is it requires less current to produce that power. What's the disadvantage of high voltage? It's dangerous. So what do? The closer so these high tension lines, they're way up in the air because they're using air as insulator. And the insulation of air varies, right? You understand? It's a good insulator, but it varies with moisture. So they get them and Alabama Power is referenced to earth ground, so that wire that power is trying to get to ground, so we have to insulate it. We insulate it with air, but they get it up way high, right? You understand? And of course, the closer they get to me, they have to start getting it what? Closer and closer to ground. What do they start doing? They drop the voltage down and that with what? With transformers. And of course, when it gets to my house, what's the two primary voltages we get at our house? Yeah, what we call 120 and 240. So all our high wattage loads runs off of 240. Keep the amperage down, which means I can use smaller gauge wire, which means now I can run it through my walls instead of running it out underground, right? Understand? All our other devices are hooked up to are designed around 120. So what advantage does low voltage have over high voltage? Safer. What advantage does high voltage have over low voltage? The big less current to produce the power. Y'all understand that? So that's why that's why we transmit AC. So Alabama Power does not make DC. If they transmitted DC, then they couldn't step the voltage up or step it down. Edison was this guy. He was a watt guy. He was a DC guy. And Tesla was a what? AC guy. And those guys fought. You need to watch the video, and I might put it on a link to it called The History of Electricity. They talk about the battle of the currents, where Edison was trying to prove that AC was so much more dangerous. He was electrocuting elephants and stuff. He was killing animals with AC. But Edison, we had to have a power plant every mile, because when they tried to push that current through conductors, the conductors would lose so much voltage they'd have to have a power plant every mile. So they'd literally have to have a boiler and a generator every mile. So AC, I can do what with AC? Well, AC, I can step it up for what? Transmission, and step it down. So we get our power from Tennessee Valley. This is Bessemer's TVA. It was some deal that when the steel industry was real big in Bessemer used to have a steel mill there, and it was real big. They went with TVA to transmit power down here, and ever since then we've still been on TVA. But if you think about it, if I transmit at 750,000 volts, then I can send 750,000 watts of power with 1 amp current. But 750,000 volts, I would probably have to keep that up 50, quite a real high, right? You understand? So that's why. It depends. They have what they call interstate lines. They have what they call intrastate lines. They have local lines. And how far they go depends on what voltage they use.
The baseline is like 50K, and then for every other kilovolt, it's like
A foot up, yeah. So it's you mean as far as the height of the cables?
yeah, as far as how high it is.
Well, what we get when we transfer power is power is equal to V times I. When it's three-phase, power is equal to V times I times the square root of 3. So that means what we can, for less current, we can send more power if we send it three-phase. So this is why when we transmit power, they usually transmit three-phase instead of single-phase. But three-phase is a lot more expensive because I have to use at least what? Three conductors. Can't you imagine 3 conductors going everywhere we have power? It would be wonderful, but it would be very expensive. So low wattage loads like our house has no need for three-phase. So our house gets single-phase power. Big industries, high power demands, they give them three-phase because it's now don't change your bill because you don't pay for three-phase, you pay for watts. This square root of 3 comes into phase during transmission, right? You understand that? So this is three-phase. These are three-phase power lines. We've all seen these. 1, 2, 3, 3 wires. Or usually they run in groups of 3s. And why they do that is they spread the load over multiple conductors. So here's the power formula right here. For AC, three-phase, V times I times the square root of 3, or I would be equal to V times I times the square root of 3, V times I times the square root of 3. Well, current flows through resistance of a conductor, we already talked about that. Higher voltage pushes less current, right? You understand that? Which means we have less line loss. So these are three-phase transformers. These are substations. What's the function of the substation? Change the voltage. It's either going to step it up for transmission or step it down for distribution, right? You understand? So extremely high voltage for transmission, a lower voltage for distribution. So usually on your power lines out there on your house, it's a couple of thousand volts. Still very dangerous. A couple thousand volts. And then you'll have a transformer out there close to your house. It's either going to be they're either going to run the cables underground if you in a community that's costs a lot of money to live in, or they're going to have a pole out there, right, a power pole out there, and it's going to have a transformer up there, and that's going to step it down for safety, so before they bring it into your house. So substations are either going to step the voltage up for transmission or step it down for distribution. That's what they do. This is typically the way Alabama Power works. So here I'm going to turn on 1,000 watts, and it's going to require 8.3 volts, 1,000 watts, and 120 volts. Out there on my distribution lines, it's running at 2,300 volts. So now in there, they're going to be 435 milliamps to get the same work, right? You understand? But it's at a watt. It's at a higher voltage. Then over here on my transmission lines, here I'm using 275,000 volts, so this would be an intrastate transmission line. Now I'm dealing with 3.6 millivolts to get 1,000 watts at my house. Then I come over here, and right here, they're generating 2,300 volts. It's pretty standard for the power company. They don't want to try to generate really, really high voltages because of the generators themselves, the wires, and the closeness of the wires inside the generator. So they're back up to 434 milliamps. So what's really neat, 3.6 milliamps send 1,000 watts of power. So that's what we have to understand. Alabama Power is not selling you current. They're not selling your voltage. They're selling you what? Power. That's why they're called the power company. And what is power, though? Power is work, right? You understand that, which is pretty neat. So this is one big advantage AC has over DC, is that we can send a lot of power with less current if we step the voltage up. Everybody okay? Yeah. This is how we do it. This is status voltage. I think this goes to 1245, right? 1245. This status voltage of an AC waveform is constantly changing. The DC voltage average of a complete cycle is 0 volts. This is very, very strange. So let's pause our lecture. So if I come over here and have a sine wave, and then if I take the average, if this plus 1 right here, and then over here I have a watt. Over here I have a minus 1. Well, what happens is your plus 1 and your minus 1 do what? They cancel each other out. But if I was to come over here and square this, this would be 1. If I square this, this would be a plus 1. And if this right here was 2, if I squared this would be 4. If I squared a minus 2, it would be plus 4. So anytime you square a negative number, it becomes positive. Okay. So once I square, so if I do this with a lot of spots along this line right here and along that line right there, and I add them together, which means, okay, I add them together, and then I take the average. Another name for average is mean. Root, mean, squared. So it's kind of backwards. And then what I do is when I get that mean, it's going to be off because I added squares. And if we come up here and take the square root of that, then we get the actual, what we call the effective voltage. So basically, RMS means the square root of the average of the squares. The square root of the mean of the square. So what happened is this is turned into RMS, which stands for root mean squared. So this is what my meter's doing. My meter is giving me the RMS value. So most people, when they talk about AC, if they don't say RMS, it is RMS. So if I was to measure this peak voltage right here, this is almost 149 volts. And this would be a negative 149 volts. But it would measure 120 volts because that's the amount of work we're getting, right? You understand? By the way, RMS means if I was to put 120 volts RMS on a resistor, and then I put 120 volts DC on that same resistor, I would get exactly the same amount of work. So my meter, most meters don't do that. If it's a sine wave, what we can do is we can take the positive peak voltage, we call it V peak, and multiply that by 0.707, and then that gives me RMS. So instead of my meter calculating RMS, what most meters do is just take the input and multiply it by 0.707. Unless you have what we call a true RMS meter. Now, a true RMS meter has a microprocessor inside of it. And what does it do? It calculates RMS. It calculates the root mean squared. If you're going to deal with non-sinusoidal waveforms that are AC, but they're not a sine wave, then you need a true RMS meter. If you deal with AC, regular Alabama Power AC, if you're an electrician, if you buy a true RMS meter, you're just wasting your money. Because they usually cost at least 2 times the other meters. So it's up to you. In our classes, you have no need for a true RMS meter. If you're working in very few places, do you need that? If you're working on circuits that do what we call pulse width modulation, you probably need a true RMS meter. If you're working with, which would be variable speed drives, AC drives. Now, if you're working with variable speed AC drives, and you put a regular meter across there, it's going to give you the wrong voltage that your motor actually sees. So I think, yeah, y'all have some variable frequency drives over there, right? Huh? Yeah, but Revere is a control company. They make controls. Johnson Electric. We got one. Ours came from Johnson Electric though, which is no longer in business. They sold out. Did they buy? Didn't say. I think y'all did. So their variable speed drives is y'all's now, right? They donated one to the college, by the way. All our variable speed drives that's been donated runs off 440. Guess what? We don't have at the college. 440, unless we put a transformer. They donated 120 volt 3-phase variable speed drive to us. That's the only one I know. So true RMS meters calculate the root of the means of the squares with correctly measure RMS values of waveforms that are not sine waves. So 120 volts RMS produces the same work as 120 volts DC, making to a resistive load. So meters measure RMS, scopes measure peak to peak. So that's one advantage of an oscilloscope. An oscilloscope shows you what's there. It don't do any averaging, it don't do any RMS, it shows you exactly what's there. All your meters are going to average. So if I've got a DC waveform that's got a lot of noise on it, which could cause problems in a computer, your meter won't show you that. But a scope will, right? And of course they say a picture's worth 1,000 words. So we'll skip over this. Everybody okay with resistance? So resistance is opposition to current flow that does not change with frequency. All opposition in a DC circuit is resistance. DC does not have a frequency component. By the way, on a test, be careful because there's one question on several of our tests saying what's the difference between AC and DC, and one of them says DC voltage doesn't change. That's false. We have DC all. My battery puts out 12 volts. Yeah, it's the same. It's not the same. It might be the same in a circuit, but it's all over the place. Reactance. Now we got to work about reactance in this class. Now whether you really understand this in this class is not extremely important. You're not going to have to do any math, but you need to understand what's going on. Unlike resistance, reactance varies with what? Frequency. So reactance only comes into play in an AC circuit. In devices called capacitors, as frequency goes up, capacitive reactance goes down. In devices called inductors, as frequency goes up, inductive reactance goes up. So we have these formulas. So so we have Ohm's law says V is equal to I times R. In real life, it's this. It's V is equal to I times ohms. Because capacitive reactance and inductive reactance vary with frequency, but they're still opposition. So opposition in a circuit is ohms, period. Whether it's reactive opposition or resistive opposition. So you can take all your Ohm's law formulas and instead of putting R, put ohms. And that now they would be true. Now notice what happens. So on inductors, if as frequency goes up, opposition goes down. On inductors, as frequency goes up, opposition goes up. So notice these guys are exactly opposite of each other. Are we okay? You okay, James? I know you got access to these PowerPoints, right?
I hope so.
Huh?
I tried to pay
No, you get access to Blackboard as soon as you're in the class.
I tried it yesterday.
Well, you wasn't in the class. When did you get in the class? And when did you try Blackboard? Now you have to understand Blackboard, the users in Blackboard is not coupled to registration. The computer division has to transfer the names from registration over to Blackboard. And they do that once a day. So odds are you got in there before you got in Blackboard, but you were in the class. So you should have access now. Huh? Syllabus agreement is due today, but you can and all the other stuff is due before. Who taught you EEP 100? You say? Donnell Perry? It wasn't the class he passed away in. Did you take in his class when he passed? He had y'all do all that, right? Syllabus agreements and all that? This is not important. We're going to see this formula, and this is in the first, when we start talking about conductors. We're going to see this formula, but it's not a formula that you have to know. Now, when you take AC, you'll have this formula. But capacitors consist of two conductors that are separated by an insulator. So what I'm going to do is I'm going to switch back over to my camera. And all I've got here is I got my oscilloscope. And here's a conductor coming out of my function generator. Here's a conductor that's coming oops, this is my oscilloscope. Okay. Let me take it out, put it on sine wave. So these guys are not touching each other. I want y'all to look at these. Here's my function generator. Here's my oscilloscope. Not this one. Can y'all see my oscilloscope? Yeah. Here's my here's my oscilloscope, sorry. Here's my function generator. So how am I getting my voltage from this guy to that guy? Now notice this. Now it hasn't, but we're not getting it through induction, because if I was going to get it through induction, I would have to have a coil of wire. What I'm doing is I'm making a capacitor. So here's my insulator, right? You understand? Here's one conductor. We call these plates. Here's my other conductor, and I'm going to come up here. I'm out here now, and I'm going to bring it close. Now notice the closer I get it, the more coupling we get. The further I get it away, the less coupling I get. And the next thing I'm going to do is I'm going to come over here and I'm going to reduce the contact area. Can you see it going down? See it going up? See it going down? All I'm doing is changing the amount that these two things overlap. See that? So what I've done is I've created a capacitor. By the way, this is the way a capacitive sensor works too. So what I've done, I've created a capacitor. Now I'm creating it on purpose, But you got to understand, any two conductors that run side by side, and if we don't do something, that's going to be a capacitor. Now, what determines the amount of capacitance is how close I can get these plates together. What I'm using as an insulator, here we're using air as an insulator. How close I can get them together. So look, the closer I can get it together, the more that gets through. And of course, the next thing is the size of the overlap. We say the size of the plate. So if I make the overlap smaller, look, it goes down. If I make it bigger, it goes up. I'm not changing the distance. So if I can produce these things, and they have an effect on life. So, but we create capacitors because they have a function. But we also get what we call stray capacitance, which means anytime I've got two conductors that are close to each other, then they're going to have they call crosstalk or capacitive induction. Capacitive coupling is what they call it. So that's the formula. So these guys, the size of what determines the amount of capacity is graded in something called parity. And that's that C over there. So F would be what? Frequency, 2 pi. In AC, you'll learn why we use 2 pi a lot. 2 pi, of course, we use 6.28 times the frequency times the capacitance. So once I buy a capacitor, what determines the amount of capacitance is how close I can get those plates together without them touching, because they got to have an insulator in the center of them. And then, of course, how the size of the plates, how much overlap do we get? I'll go over there and find a variable capacitor, and you can see how it adjusts. So we have variable capacitors, and what we're doing on a variable capacitor is we're either adjusting what? The distance between the plates, or we're adjusting the size of the plate. But what I want you to see is when frequency goes up, what happens to opposition? It goes down, right? Y'all understand that? And we'll show y'all something when we get back, what the other problems we have. So what we're going to do in the next class is we're going to take a inductor or a capacitor and then put it in series with something and see what strange things happen in an AC circuit that don't happen in a DC circuit. This. So guys, we got, and I'll get that other part of the lecture up there, James, so you can look at it. PowerPoints are probably already up there. Let me make sure. This site was copied over, so I want to make sure. If it's still working. So it should be in course content. If I didn't log me off. It didn't. And then lecture slides. And this lecture slide's in copper, by the way, so that's what we're talking. We're talking about copper. No, introduction. I believe I got it out here by itself. So here's the PowerPoint. And we're way down here on what PowerPoint? Way down here somewhere. And I'll go ahead and figure out which one that lecture is, and I'll put it up there in that recorded lecture before I leave today. And I'll put it, well, it'll be tonight, because what I have to do is I have to upload it to YouTube, and then I have to link it through the college website. By the way, on YouTube, you can search for me, Rich Raymond, and all the recorded lectures should be up there, but it's going to be a lot of them. So you'd have to find this one. Are we okay? Yeah. All right, guys. Have a good weekend. Maybe James will show up. Nice having you in the class. We got 2 Jameses.
Actually, you take the Lord's name on it.
Yeah, well, yeah, I did.
Oh, Mike, my middle name is James. Some people call me James.
Okay, I thought you.
No, Mike.
Well, then I'll call you Mike then. That way we only have two So I got you confused when I said James wasn't here, right?
Look, I am here.
It's like Thomas. Thomas goes by two names. His middle name's Wesley.
Everyone at work calls me Wesley.
And when I ask you which you prefer, what do you tell me?
Either or.
Yeah, I don't care. You can call me Ray. You can call me Jay. You can call me RJ. That used to be a comedian.
Yeah.
But you don't have to call me Johnson. That's an old comedian. It'd go on for a long time. You can call me Ray. You can call me Jay. You can call me RJ. His name was John Johnson or something. Okay, guys.